Okay, so last week we saw how a linear differential equation of order n can be transformed to the system of first order differential equations. And so from this transformation, we saw that really each linear differential equation of order n has n parametric family of solutions. This refers to the homogeneous part. And then if we find also one particular solution for the non-homogeneous part refers to this f, which is non-zero. Then the solution to this non-homogeneous differential equation is a sum of a solution of a homogeneous part and a particular solution. To determine the unknown constants, we need one additional condition, which gives us n equations. So we expect n-dimensional space of solutions of the homogeneous part. And let's say that we have found n solutions, and we would like to determine if they are really the linear span of the space of solutions. To answer this problem, the Wronskian determinant is needed. So the Wronskian determinant is formed. So the Wronskian matrix is formed so that we have n solutions. We put them in the first row, and then in the second row we plug in the first derivatives of those solutions up to the last row, where we plug in n minus first derivatives of the solutions. And this is a determinant function, which means that it's dependent on the time, on this t. So we compute this Wronskian and its determinant for each specific t. And in general, it's not true that if for some t this determinant is non-zero, it should be non-zero for all other t's. So in general, it's very easy to find examples where this won't be true. However, if we are working with differential equations, the main result of the theory is that if the Wronskian is non-zero, the determinant of the Wronskian is non-zero in one point, then it's non-zero in all the other points. To prove this result, one needs to observe that the Wronskian determinant, which is a function of t, satisfies one specific differential equation, one specific linear differential equation. This is that one. So phi prime is minus the coefficient at the n minus first derivative times phi. And in fact, to derive this differential equation, it requires only working with the specific formula for the determinant. So this is specific formula for the determinant, which you've told me you didn't see, so we didn't go thoroughly through this proof, but this is the specific formula for the determinant. Differentiating this formula using chain rule and using some properties of the determinant, like if you have two linearly dependent rows, then the determinant is zero. So this is the only thing which we need to use here in this calculation. So it turns out that the Wronskian satisfies this differential equation. We know from a few previous lectures that this differential equation can be easily solved by separation of variables. And this gives us our result. So since the solution is of this form, we see that plugging different t's in the solution, it's always zero or never, which proves this result. So when you have n solutions to the differential equation, you only plug in one value of t. Look if the Wronskian matrix is invertible, which is equivalent to saying that the determinant is non-zero. And then you know that you have the whole family of solutions to your differential equation. Okay, this was first part of last lecture. And then we focused on the case where we have constant coefficients in our differential equations. So those a, n, ai's are not functions of t, but are just real numbers. In this case, when we transform our differential equation into the system, the matrix of the system is, that one is so-called companion matrix. And it's easy to see that the determinant of this companion matrix is just is so-called characteristic polynomial, which is obtained just by replacing ith derivative with lambda to the power of I in our differential equation. So this proves that we only need to solve nth order differential equation, we only need to replace ith derivatives with lambda to the power of I, then compute the roots of this polynomial, and then the solutions are of this form. So e to lambda t, where lambda is a root, times so e to lambda t, where lambda is a root, times some constant. This is in case where the root is real, so where lambda is real. If lambda is not real, then we know that the solutions, the roots of the characteristic polynomials will occur in complex conjugate pairs, alpha plus minus I beta. And taking the real part of e to lambda t and the imaginary part gives us two real solutions to our differential equation. These are e to alpha t cosine beta t and e to alpha t sine beta t. While if lambda is a multiple root of the differential equation, then the solutions would be e to lambda t, e to lambda t, e to lambda t, and so on. But they are not different. But it turns out by a short calculation that in this case, if lambda is a root of multiplicity k, then all solutions are e to lambda t, then t times e to lambda t up to t to k minus 1 e to lambda t. So except e to lambda t, we get this k minus 1 additional solutions where we just multiply by t to the power. To check this, it's only a short computation. So it's written on this slide. We didn't go through this, but if you're interested, you can go through this. And the only non-trivial part here in this calculation is, so you have this operator L is in fact the operator which defines the left-hand side of our differential equation. So we see our differential equation is that one, and we just to this differential equation we define the linear operator which is defined by L on the function u is nth derivative of u plus and so on plus a0 times u. And then plugging into this differential equation into this operator t to q times e to lambda t, where q is smaller than the multiplicity of the root lambda as the multiplicity of lambda as the root of the characteristic polynomial. Plugging this into this definition, and then the only non-trivial thing is here to exchange the derivative with respect to t and the derivative with respect to lambda. So here you notice that we can notice that t to q times e to lambda t is in fact qth derivative of e to lambda t, because when we take the first derivative, we get t times e to lambda t. When we take another derivative, we get t squared times e to lambda t, and so on. So instead of t to q times e to lambda t, we can plug here this differential operator. And then we plug in this differential operator in the initial differential equation. So if we will observe this term, for example, nth derivative of u. This will be, in fact, nth derivative of qth derivative, but nth derivative would be with respect to t, while qth derivative will be with respect to lambda. So this is here. But then you know from analysis that we can, if everything is nice, which is in our case, the function e to lambda t is nice, it's continuously differentiable, so there is nothing to worry about. We can exchange the derivative with respect to t with the derivative with respect to q. So we first differentiate with respect to t and then with respect to q. This is this step, this equality. And then what we get here is, again, characteristic polynomial of the differential equation times e to lambda t. And since lambda is the root of multiplicity k of our polynomial, we know that when we will differentiate it with respect to q, where q is smaller than k, we will get 0. So the only non-trivial part here in this calculation is that we replaced, so we first noticed that t to q times e to lambda t can be written as this differential operator, and then we exchanged the order of derivation with respect to t and lambda. Okay. And then we focused on second order differential equations with constant coefficients. So in this case, the solutions are either e to lambda t or e to alpha t times cosine beta t, where alpha plus I beta is lambda. Or if lambda is a double root, then the solutions are e to lambda t times and t times e to lambda t. So this refers to second order differential equations which are homogeneous. If they are not homogeneous, then we have to find also a particular solution. And in some cases, it's very easy to guess one of the solutions. And we looked at the end, we looked at a few examples. So the first example was when we have a polynomial on the right-hand side. And we noticed that, okay, so what would be the particular solution? It should be of the form which will still give us polynomial when we compute the left-hand side. So when we take the derivative and the second derivative, it should still remain a polynomial. Therefore, some sensible guess would be that the particular solution is a quadratic polynomial. And plugging this into the differential equation, comparing the terms at t squared, at t, and at 1 gives us a system of 3 linear equations in 3 unknowns. Therefore, it will be solvable. So the second case was when the right-hand side is exponential function to some power. Still, when we take the derivative of the left-hand side, we should still get the function of the same form. And the candidate is then the same exponential function, because we know that when we take the derivative of the exponential function, nothing happens, only the constant in the exponent jumps in front. So the guess would be that the solution is the form a some constant times the same exponential function. Plugging this into differential equation and computing the unknown constant gives us particular solution. So this works well if on the right-hand side we have an exponential function to the power, where in the power we don't have a 0 of the characteristic polynomial. So if we look at the homogeneous equation, what are the zeros of the corresponding characteristic polynomial of this left-hand side? Yes, -2 and -1, and they are not equal to 3. therefore this procedure works. So if 3 would be the solution of the homogeneous part, what would happen when we plug in this particular solution into the left-hand side? What would we get as the result of the left-hand side? For example, if so you've said that -1 and -2 are the solutions of the homogeneous part. So if I plug in a times e to -1t into the left-hand side, what do I get? 0, yeah, 0, because it's the solution of the homogeneous part. So if on the right-hand side we have -1t in the exponent, this procedure won't work. However, in this case, it turns out that if we add t times e to this function, then the procedure works. And this is the concept of the next example. So second derivative of x minus x is e to t. At first look, we would guess that the solution is a times e to t, the particular solution. But since 1 is also the solution of the homogeneous part, so is the root of the characteristic polynomial, plugging this particular solution on the left-hand side will give us 0. However, we have to a little bit correct the form of the solution, and it turns out that if we add t times e to t, this will work. Okay, this is where we remained last time, and now we will look at one example where we can't guess what's the form of the general solution, but there is a procedure to determine it using variation of constants. So let's look at this specific example. We will have a differential equation x double prime plus x is equal to 1 over cosine of t. So the right-hand side is not of the form which would allow us to guess what would be the proper solution. I can mention here something which I haven't mentioned before. So if on the right-hand side we would have cosine t, so just intermezzo, because we will also use this later on. If the right side is cosine of t, what would be the guess? For the particular solution? Do you have any suggestion? So on the right-hand side, we have cosine t, and the guess for the solution should be something which on the left-hand side, when we take the first derivative and the second derivative, still remains of the same form. So still remains some trigonometric function. So what would you guess for the particular solution? Yes, yes. So because the second derivative of trigonometric function cosine and sine remains cosine and psi. This sine, this is a good guess, yeah, and Matei also notice this in chat. So a times cosine t plus b times sine t would be a good guess in general. It always works when we have trigonometric functions. Okay, this is one intermezzo and another intermezzo. Let us say that we know a particular solution for x for some second order differential equation, ax double prime plus bx prime plus c is equal to some function f1 of t. And we will denote the particular solution by, let's say, xp1 of t. And now we take the same homogeneous part, but change the right-hand side. Now we have a differential equation, ax double prime plus bx prime plus c is equal to f2t. So what we notice is that both left sides are the same. And let's say that we also know the solution to this second non-homogeneous dE, which is xp2 of t. So what is then the solution to ax double prime plus bx prime plus c is equal to f1 of t plus f2 of t? So I took again the same left-hand side, but on the right-hand side, I just sum up together both non-homogeneous parts. So what would you guess would be the solution to this new differential equation? Yes, so just their sum, xp1 and plus xp2. And what's the reason for this? So what kind of operator is differentiation? What is the property? One property which ensures that this will be really true. That so we claim that xp of t is just xp1 of t plus xp2 of t. So it's easy to see. Just we just plug in this right-hand side. So we just plug in this into our differential equation and see that we get we can separate xp1 and xp2, and from xp1 we get f1, and from xp2 we get f2. So what's the crucial property of differentiation which ensures that this works? Yes, it's linear. So linearity, because of linearity. So this computation works because differential operator or differentiation operator is linear. This means that if we take a sum of two functions and differentiate, then we get f prime plus g prime. So, however, is differential operator multiplicative? No. Yes, product rule. Yeah. So, but it's not. Differentiation operator is not multiplicative. F times G, and then taking differentiating is not F prime times G prime. So this is not the case. So it is in fact using product rule. It's F prime G plus FG prime. So those are trivial things, but why am I mentioning them? We can use this for solving differential equation, when we have on the right hand side sums of functions, what does this tell us? So let's say that we have a differential equation, and on the right hand side, on the non-homogeneous part, we have sums of different functions. So how would you try to find a particular solution? Yes, you can find the solution for each of them. Yeah, and so it's enough that we study how to find the solution to one of them, because then we will also know how to find the solution to the sum of them. So we can, so this shows that it is easy to find a particular solution to f1x plus f2x plus so on plus fmx as a non-homogeneous part. So this sum is our non-homogeneous part. So it is enough to find the particular solution to each of them and then sum together, sum up them together. So to each summand and sum up together. Yeah. These were two intermezzos which I forgot to tell about before. So f1 plus f2. Yeah, this was our so sum. So if you have, for example, if you have a polynomial as f1, we know how to solve it. And if you have exponential function or a trigonometric function as f2, then we also know how to solve it. And so then we have the particular solution for this sum. However, if we have a product here, then we won't know how what would be the proper solution, knowing only the solution to each of the factors, because we have here that the differentiation operator is not multiplicative. So if it was multiplicative, then it would be easy. But since it's not, having here product of functions is not that easy to determine the particular solution, even if we know the solution to each particular factor. Okay, now let's return to the example above. So in this example, we have, as a non-homogeneous part, we have 1 over cosine of t. And so it's difficult to figure out without any computation what's the appropriate form of x. So on the left-hand side, we need something which will still remain 1 over cosine of t or something similar when we take the second derivative. And it's not clear what would that be. Maybe you can try guessing and have luck, or so do some intelligent guessing, but here is a better way how to tackle such a problem without guessing, and it's called variation of constants. So if you remember from first order DEs, how we did the variation of constants. So do you remember what we did? Yes. So we solved homogeneous part, and then instead of the coefficient, we plugged in a function, and then we plugged in this into our initial differential equation, and it turns out that this function can be explicitly obtained just by integrating, so just by solving the differential equation in this unknown function. Let's try to do this here. So let's first solve, we solve the homogeneous part. And we know that the homogeneous part will have two parametric solution. xp of t, x h of t is some constant times the first solution plus some constant times the second solution. And now we do the same trick. We just replace, for the particular solution, we just replace those two constants by functions. So we have here C1 of t and C2 of t, and x1t and x2t remain where they are. And now we try to plug this into our differential equation. But before doing this, let's compute. So we will need the first derivative of this particular solution and the second derivative. Let's first compute the first derivative, and we will see what's happening. So xp prime of t is, now we use the product rule. So we have C1 times x1, both are functions of t. So we differentiate C1 and rewrite x1, and then we rewrite C1 and differentiate x1. And the same for C2. So we get here 4 terms. If we repeat this procedure, when computing the second derivative, how many terms will we obtain? 8. 8 in general. Some of them will be of the same form, so they will just sum up together, but there will be too many terms to determine explicitly what's the solution. So we will have a lot of freedom, and it will be difficult to know what to do. And it turns out that here we can do some, so since we have 2 parameters, if we only have, so if we only plug this into our differential equation, initial differential equation, we have 2 unknown functions and 1 equation. So we will have 1 degree of freedom. That's why we can do another reduction, because we have 2 unknown functions. We can introduce new equation, and we try to get rid of some terms here in the first derivative. And it turns out that if we take the derivatives of C1 and C2, so if we take this part and this part and just put their sum to be 0, it turns out that the procedure works. So C1 prime of t x1 plus C2 prime of t x2 is 0. So we add this. There is nothing wrong with adding this. If this equation leads us to some, if this equation leads us to some contradiction, this only means, this doesn't mean that the particular solution doesn't exist. This only means that this reduction was not the right one. So we should then try to do another reduction. But it turns out that this reduction always leads to the solution. So we add this condition, and it turns out that it always works, as we will see shortly. So we could continue. For now, we haven't used our specific differential equation yet. So we could continue with this calculation in general, and we would see that C1 and C2 can be explicitly determined. But let's focus now on the specific equation. So let's start working with our specific equation so that we will see this technique, variation of constants, on this example, which we have. So we have x double prime plus x is 1 over cosine of t. So the homogeneous part is x double prime plus x is equal to 0. And then the characteristic polynomial is lambda squared plus 1 is equal to 0. So when you introduce the characteristic polynomial, don't make a mistake. So you shouldn't plug x to be lambda, but x is in fact 1 and x prime is lambda. So I did this mistake last time. You would shortly notice that it is a mistake, but yeah, x is in fact 1 and not lambda. So lambda squared plus 1 has two solutions. So lambda is I and lambda 2 is minus I. But we would like to have real solutions. So how do we get real solutions out of this complex conjugate pair? What are then real solutions? So complex solutions would be x1 of t is, I will write here c, so it would be e to it, and x2 c of t is e to minus it. But we know how to produce real solutions out of this. Sorry? We need two solutions. Or Euler formula, yeah, Euler formula. So e to it is cosine t plus I times sine t. And e to minus t is cosine t minus I times sine t. And we saw that we can just take the real part and the imaginary part of this solution, because summing up them together gives us cosine, and subtracting and dividing by 2i gives us sinus, so the real part, the imaginary part. So the real solutions are then cosine t and sine t. So the solution to the homogeneous part is then a times cosine t plus b times sine t. This is the solution to the homogeneous part. So the particular solution is obtained by variation of constants, as we did above. xp of t is a of t cosine t plus bt sine t. And so we took the first derivative of this particular solution. And from this first derivative, we have we added another condition. So in our case, it would be a prime of t cosine t plus b prime of t sine t is equal to 0. So the derivative of this particular solution are only those two terms. So the first is at times derivative of cosine, and the second is b of t times derivative of sine. So xp derivative of t is then at times derivative of cosine plus bt times derivative of sine, which is minus at sine t plus bt cosine t. And this is true under the condition that a prime of t cosine t plus b prime of t sine t is equal to 0. This was our condition we added. And from now on, everything will be only computation. So from now on, it will be we will determine a and b explicitly. So we take the second derivative of particular solution. Now we really get 4 terms again. So it's minus a prime, and I won't write t again to shorten the notation. So sine t minus a times cos, so derivative of sine is cosine, plus, and then derivative of b times cosine minus b times derivative of cosine is sine minus sine. That's why I wrote here minus. Okay, and now we plug everything into the dE. So xp double prime plus xp should be equal to 1 over cosine of t. So we have minus a prime sine t. So before doing this, let's notice that we have here, so from here, from this condition, we can get rid of a prime or b prime. We can express b prime out of this condition or a prime out of this condition. So let's express, for example, b prime so b prime is minus a prime cosine t over sinus t. Okay, and I will just use this when I plug this into our dE. So xp double prime is then minus a prime sinus t minus a cosine t plus, and instead of b prime, I write minus a prime cosine t over sine t times cosine t minus b sine t. I can't get rid of this b yet. And then plus xp, which is xp was a cosine t. Sorry, I think it was a sine t. No, it was a cosine t plus b sine t. And it should be equal to the right-hand side, which is 1 over cosine t. So I'm plugging this, our expressions into this dE. And if we look at this, we notice that b sine t cancels out. This is not a coincidence. Doing this for a general differential equation, not a specific one, would give us the same. So the terms containing b cancel out. So everything what remains is the terms containing a. Also, this linear term in a cancels out. So what remains is this term containing the derivative of a. What can we do here? So we have a prime. We can factor out a prime from the left-hand side, minus a prime, in fact. And what we get, to put everything on the same denominator, we have sine t. So the denominator is sine t. So the first term is multiplied by sine t. So we get sine t squared plus cosine squared over sine is equal to 1 over cosine. So what is it's here. Yeah, but thank you for noticing. I could easily make a mistake. So in the numerator, we get 1 because sine squared plus cosine squared is 1. So the differential equation in A is then a prime is minus sine t over cosine t. You see that it's quite a lot of computation, but in fact, we can do it to the end. So what's then a of t? A of t is integral of the right-hand side. So on the right-hand side, we have integral of tangents, but how to integrate this right-hand side? One way would be just to look in the tables with indefinite integrals of trigonometric functions. But if we just try to remember how to integrate sine over cosine. Yes, which one? If we replace sine by u, then we won't get cosine in the right in the right place. Because if we replace sine by u, we'll get we should have cosine in the numerator, but we have it in the denominator. So we should replace the new variable should be cosine t, so that du is then minus sine t dt, and this is really what we have here in the numerator. So it is integral of du over u. So it's integral of 1 over u is logarithm of absolute value of u. So it's logarithm of absolute value of cosine t. So we really obtained a. How do we obtain b out of this? We still need b. Yeah. So we can plug now a prime. In fact, we didn't even need a. We just needed a prime. We have here a prime. So if we plug this a prime in above to this expression, where we express b prime, we will also get a differential equation for b prime. So let's do it here. B prime will be minus so sine t minus sine t over cosine t times cosine t over sine t. So in fact, we get 1. So b is then b prime is 1, which means that b is bt is just t. I think it's +1 because we have here minus a prime, and then in the differential equation for a prime we get minus. Just one question: why don't we need? Why I just wrote bt is t? Why I just neglected the constant? Why don't we? Why do we? Why can we neglect the constant? In fact, you remember from calculus, it should be b of t should be t plus some constant c. But why can I just forget? Why can just plug c equals to 0? Yes, yes. The constant will go away. It will be in fact part of the homogeneous solution. So if we look x particular, xp of t is so we said it was homogeneous part was c1 x1 plus x2 times c2, and then x particular is c1 t x1 plus c2 t x2. So this constant, okay, let's say a and b to stick to the same notation. Sorry, so a and b. So this constant here in b would in fact be a part of the homogeneous solution. So if we have here t plus c, this cx2 will be in fact a part of the solution of the homogeneous part. So we really need only one solution to the one particular solution. It really doesn't matter which one we take, because every constant part will be a part of the homogeneous solution and will be determined after we plug in initial conditions. That's why when I do indefinite integration, I can just forget about the constants. Also here, I just forgot about the constant when I computed a. So the final solution, particular solution, is then a of t times cosine plus b of t times sine. So it is logarithm of absolute value of cosine times cosine plus t times sine t. So you see from the initial non-homogeneous part was quite easy, 1 over cosine, but we don't have a lot of chance to just guess this particular solution. So, but variation of constants, it always works. So we can always, when doing a variation of constants, we can always assume that what we did here, c1 prime times x1 plus c2 prime x2 is equal to 0. Why can we always do it? So I didn't want to do all the computations from here below with a general DE, but if we did all the computations with the general DE, not with 1 over cosine of t, everything would work the same. So in this step, we would express b prime out of a prime and some function, and then plugging into our initial differential equation, we would here get differential equation in a prime. In fact, it would turn out that in the denominator we get Wronskian, but Wronskian is non-zero. That's why we really can compute the the denominator. Okay. Are there any questions regarding this example? Okay, let's do a 15-minute break. I think it's a good point to do a break, and then we go over vibrating systems shortly, and then we start preparations for the exam. So let's continue. What remains are 4 types of vibrating systems. They are all described by second-order differential equations, and maybe we just go through those PDFs, PowerPoints, because everything is just computation. And the main point is to see different notions of the limiting behavior in these vibrating systems. So we'll see one occurrence of a resonance, which is different from the other solutions, but in all other solutions, the vibration stops at some point. So the first case, we have vibration. So we have a spring attached to the ceiling. Maybe I can, so that you will easier follow, I can draw a picture, and then we return to the slide. So we have our situation that we have a ceiling, we have a spring. Let's say that this spring is of length L, but then we attach a mass, some weight of mass M, some object of mass M to this spring, and of course this spring then stretches a little bit for some D. So at the end we have spring stretched for D, and this is the mass M. So let's say that this is the equilibrium position. What are the forces acting on our mass? Yes, gravity and the force of the spring. So gravity, we all remember from high school that gravity is mass times gravitational constant. And there is also one law, physical law, which describes the force of the spring. Do you remember how it's called? K times D, yes. But how is this law called? Hooke's law, yeah. But yeah, it's K times D in size. So the mass of the force of the spring is just the opposite, just in the opposite direction to the gravity. And it's the force of the spring is K times, in size it's K times K times D. K times the displacement, in our case it's D. And minus denotes that it's in the opposite direction. So our positive direction is downwards. So this is positive direction. So now let's say that this is our equilibrium position, that the origin is here. So this is our origin. It's x equals to 0, and we are measuring the displacement of this mass from this origin. So let's say that we stretch spring for some x. So let's say that we pull it for some x out of the equilibrium position. And what's going to happen? So what's going to happen with this mass? The spring, the force of the spring will increase because the stretch will be bigger. It will be delta x plus d. the force of the spring will increase, the force of gravity will remain the same. That's why the mass will start, the object will start to vibrate. So it will go up, and since so it will go up. Let's say it will go up and then down and then up and down, and we will see what's the solution. From the solution of this differential equation, which describes the motion of this spring, we will see what happens. Either the spring stops, or it just vibrates in infinity. So how would you describe the forces acting on the mass in this motion? So which law describes the forces of on the mass at each point? Yes, Newton's second law, which says that. Yes, so second Newton law says that sum of forces acting on our body is the same to the mass times acceleration. So acceleration in our case is just, what's acceleration in our case? Yes, second derivative of the displacement. And since we normalized our origin of x, what are in fact our forces acting on the object? So we have two forces. One is gravity, which is m times g. It doesn't depend on the displacement. What about this spring force? So it's minus k times, what's here? Minus k times. Yes, but since we put x to 0 when the spring is already stretched for d, the displacement is only delta x, because our origin is now x equals to 0. So it's in fact minus k times delta x. So, and let's say that delta x is just x, because delta x is the x value. So the distance of x value from the origin. So delta x is in fact x. Can you repeat? So that is true, but we can, so what, let's say that we have this model. Compared to this model, fg is still m times g. Yeah, gravitational force is in fact, gravitational force is a vector. And then f spring is minus k, and then as you suggested, d plus x. So d plus x. So this is the second case. Okay, yeah, in fact, this is correct one, yeah, because it cancels out m times g, in fact cancels out with k times d, but this first model would be correct if the origin would be here. So if the origin is here, x is 0, then this refers to this first model. So this x would in fact then measure the distance, I mean the displacement from this point. But if we put the origin to this point here, then we need to also add this d here. Yeah. Thank you for this correction. In any case, our system will be then the same when we plug in either the first or the second model into our second Newton law. We will get the same equation. So let's plug in this model into our second Newton's law. What we get is that gravitational force plus spring force is equal to m times the acceleration, which is second derivative of the displacement. So we will use minus when we plug in here. So we have here minus in the, since I don't have sizes here yet, I just have vectors. It can be plus, but yeah, it will be minus when I plug in the formula for the spring force. So it's m times g, and then minus k times d plus x is equal to m times the second derivative of x. And this mg minus kd cancels out. So mg minus kd, this is 0, minus kx is equal to mx double prime. So our differential equation is mx double prime plus kx is equal to 0. So this is vibration without damping. This is free vibration without any damping or external forces. Damping refers to air resistance or torsion in the spring or any other dampers. So without damping and without external forces. So external forces refers to, for example, if we insert some force on the object and insert it all the time during the motion. So what do you expect to be the solution of this differential equation? So what kind of motion do we expect? Will it stabilize? Will it stop? Or what do you expect for the spring? Sorry? Yeah, perpetual motion, always just periodic motion. Yeah, periodic motion, just going up and down, and the amplitude of the motion will be always the same. So if we move this mass for delta x at the beginning, then it will just start to vibrate for delta x below the origin, and then for delta x above the origin, and then again delta x below the origin, and so on. So this is what we expect because there are no dampers. So it's a little bit in contradiction with what we expect in real life situation, because in real life situation we have air resistance, we have spring friction. But if everything, if the only forces would be gravitational force and spring force, then this is what we expect to happen. To confirm this is true, we only need to solve this differential equation. So let's introduce omega. Probably you know from physics, omega, it's nothing else, just omega squared is k over m. It is just some new constant. but it's obtained just by dividing this system. So m x double prime plus kx is 0. We divide it by m, so that we get x double prime plus k over m times x is equal to 0. And this k over m is positive. That's why this constant is positive. And to stress that it's positive, we introduce new unknown, which is omega squared. So we need to solve the differential equation x double prime plus omega squared x is equal to 0. And let's solve this homogeneous dE. So the characteristic polynomial is lambda squared plus w squared is equal to 0. So lambda 1 is minus I times w, and lambda 2 is plus I times w, which means that the complex solutions are e2 minus I wt, and the second complex solution is e2 I wt. So what are then the real solutions? Yes. Yes. So cosine omega t, so real part of one of the solutions and imaginary part of one of the solutions. So our x of t, the solution to this homogeneous part, is then a times cosine wt plus b times sine wt and it can be also written, this can be also written so sorry, we had problems with EduROM. Hopefully now it will work. So the solution to this vibrating differential equation is this a times cosine wt plus b times sine wt. We already see that the motion is periodic, but to figure out what's the amplitude, it's convenient to rewrite this as, let's say, r times sine wt plus k. It's always possible to do this because so we have here two unknowns a and b, and I rewrote this with another two unknowns, which is r and k. So how to obtain what is r and what is k? To see how one would figure out what's r and what's k. Yes, we use addition sign for the, so the addition law for sine, which is r times, we have sine wt plus times cosine k plus r times sine k times cosine wt. So I just used here that sine of the sum is sine of the first one times cosine of the second one plus sine of the second one times cosine of the first. And now we have, so we compare the first and the third line. And what we get here is r times cosine k is b, and r times sine k is a. So how do I get r out of this? So r times cosine k is b, and r times sine k is a. So how do I get a and k out of this? Okay, yeah, we can do this. We can express r out of the first equation and plug it into the other, but it would give us the same as if we just divide those two equations, and r will divide out. So dividing gives us that, and I will divide the second one with the first one. Would give us that tangents of k is equal to a or b. So k is then arcus tangens of a or b. And now so if you're working numerically, then this is enough to get r. But if we are working symbolically, we can still say that r is a over arcus tangens of, so now it turns out that r is equal to a over sine of arcus tangens of a over b. I just plugged in k into the second equation and expressed r. But there is one easier way to obtain r. So from here, it's not seen what r is, easier expression for r. I mean, r is what's written on the right-hand side, but this right-hand side can be simplified a lot. So we can notice that if we square both of the equations, what we get, so squaring 1 and 2 gives us r squared is equal to r squared times cosine squared k is equal to b squared, and r squared sine squared k is equal to a squared. And how can I get r squared now out of this? How can I get rid of cosine and sine? Yes, so we just sum up together those two. Summing up gives us r squared times cosine squared plus sine squared is sum of squares a squared plus b squared, and cosine squared plus sine squared is in fact 1. So r squared is a squared plus b squared, so r is positive square root of a plus b squared. You see, it doesn't look the same as what we got above, but it's in fact the same. So this is proper expression, and it's the same to that one. So to prove that both are the same, one would need to express, so to compute sine of arcus tangens of a over b, and it will be possible to obtain that it's just a squared plus b squared. Okay, so the motion is really periodic. If I draw what's happening with the pendulum, let's say that this is time and this is displacement. So at the beginning, the displacement is r, because r is the amplitude of the motion, And what we're doing is just following the sign, because we rewrote the solution. We rewrote the solution as r times sine of something. So it's really sine with multiple amplitude r. In this case, is just some translation in the x-axis. Sorry, in the t-axis, because our x-axis is now in fact time. So this was the first motion. This was vibration without any damping or without any force. Then the second possibility, I won't switch to slides. I will just write on the blackboard. We add damping. So we add the force of damping to the motion. And this damping, this refers to air resistance or spring friction or other dampers. And it turns out this is again a physical model that the force of damping is proportional to the velocity. So force of damping, it opposes the motion. That's why it's minus. And it's proportional with proportionality constant beta times velocity. So velocity is in fact x derivative. So this is a model. This is a physical model, which is believed to be true. So we'll just regard it as true. So our differential equation then becomes, so before we had only force of gravity and force of spring. Now we also have a force of damping. And it is equal to m times the displacement. So mass times gravity minus force of spring was k times x. So x plus d. And minus this damping force, which is beta times x prime. And this is equal to m x double prime. Again, subtracting, so canceling mg with kd gives us a differential equation mx double prime plus beta x prime plus kx is equal to 0. So this is our differential, second order differential equation. So before we go into solving this differential equation, what do we expect? What kind of motion do we expect now? So before we had periodic motion with the same amplitude all the time, but what do we expect if we add this damping force? What will happen eventually? Yes, so we're expecting that the motion will stop in infinity. So the amplitude will be smaller and smaller, and the motion will stop. So we expect periodic motion with so periodic. I will put this into the parentheses. with periodic motion, we mean that the solution will be some linear combination of sines or cosines, but in fact it won't be periodic because the amplitude will decrease all the time. So we expect periodic motion with decreasing amplitude. Which stabilizes after enough time. Okay, and let's see if our differential equations, if the solution to this differential equation will confirm this claim. So what do we have? How to solve this dE? What's the characteristic polynomial? M times lambda squared plus b times lambda plus k. This is our characteristic polynomial. And then what are the roots of this polynomial? So we will have three different situations. Lambda 1, 2 is equal to minus beta plus minus, and then we have here beta squared minus 4 times m times k over 2m. So here I'm using this, if you have a quadratic equation, I'm using the formula for the roots of the quadratic equation. I said that we will have three different behaviors. What did I have in mind? According to the roots of this quadratic equation. So why we get three really different situations if you observe this formula? Yes. So if discriminant is bigger than 0, we have two real solutions. If discriminant is 0, we have one double real solution. And if the discriminant is negative, then we have a complex conjugate pair. So we have three situations. If beta squared minus 4mk is bigger than 0, then the eigenvalues will be real. Lambda 1 and lambda 2 are real and different to each other. And the general solution will be x of t is c1 times e to lambda 1t plus c2 times e to lambda 2t. Okay, this is the solution if the discriminant is bigger than 0. We claimed above that x of t should go to 0. We expect that x of t will go to 0 as t goes to infinity. Why is this true? Yeah, but lambda 1 times t, when t goes to infinity, can go either to plus infinity or to minus infinity. So, but if we want that x of t goes to 0, lambda 1t must go to minus infinity, and the same for lambda 2t. So why can we know that lambda 1 and lambda 2 are both negative? So for this claim, lambda 1 and lambda 2 must be negative. why is this true? How would we check that this is really true? So let's look at our differential equation. It's m lambda squared plus beta lambda plus k is equal to 0. And the only characteristic of this equation is that all three coefficients are positive, because m is mass, k is positive constant, and beta is positive constant. Okay, yeah. Yes, this is true, yeah. So beta squared minus 4mk. Yeah, this is a good observation. I thought to give another argument, but this is a better one. So beta squared minus 4mk, this is smaller. We know by assumption that it's bigger than 0, but it's smaller than beta squared. And that's why square root of beta squared minus 4mk will be smaller than beta and bigger than 0. So we see that the numerator will be negative, and both eigenvalues will be negative. Yeah, that's good observation. So yeah, okay. From the formula, we see that lambda 1 and lambda 2 are indeed a negative. Other way to see this would be to just know that m lambda squared plus beta lambda plus k, this factorizes as m times lambda minus lambda 1 times lambda minus lambda 2. And now we compare. So we have m times lambda squared plus lambda and lambda m, and here minus lambda 1 minus lambda 2, and plus m lambda squared. And we see, so we compare k and m lambda squared. Sorry, not lambda squared, lambda 1, lambda 2. So from this, we see that lambda 1, lambda 2 must be positive. The product must be positive. While from this second middle term, since beta is positive, we see that lambda 1 plus lambda 2 must be negative. So lambda 1 plus lambda 2 must be negative. So the first lambda 1, lambda 2 is bigger than 0 gives us that they are both of the same sign. But since their sum is negative, they both have to be negative. But yeah, it's even easier to see this from the formula. Okay, this was the first option where the discriminant was positive, and it's called, in this case, such motion is called overdamping. When the discriminant is 0, we have a double real root. So the second option is that beta squared minus 4mk is equal to 0, which means that lambda 1 and lambda 2 are both the same and both are real from the formula. So the discriminant is 0, which means that lambda 1 and lambda 2 are both real and the same. And so the solution is e to lambda 1t, some constant, times e to lambda 1t plus dt times e to lambda 2t. And we can just write, instead of lambda 1, lambda 2, just lambda, because they are the same. We can just write lambda is lambda 1, lambda 2. Again, we would like to see that x of t goes to 0 as t goes to infinity. So how do we know that x of t really goes to 0? Yes. So again, we see from the formula that lambda is negative. So from the formula, sorry, no, not x, lambda is minus beta over 2m, 2mk. So it's negative, which means that this first part goes to 0. What about the second part? Why does the second part also go to 0? Because it's multiplied by t. So t, when t goes to infinity, this first factor also goes to infinity. But how do we know that t times e to lambda t goes to 0? How do we know that the exponential function prevails? Do you remember from calculus, how would one check this? So what is limit as t goes to infinity of t times e to lambda t? How do we compute this? It's special limit. It's the form of this limit is infinity times 0, and we don't know which one prevails. We can use one rule to figure out which one prevails. Yes, we can use L'Hopital rule. Yeah, true. One way is to use L'Hopital rule. So it's easier to let t in the numerator and put e to lambda t in the denominator. Of course, we have to multiply by minus. And now we use L'Hopital rule. And get, so the derivative of the numerator is 1, while the derivative of the denominator is minus lambda times e to minus lambda t. And as t goes to infinity, this goes to 0. This, yeah, so the limit is 0. It's so. Yeah, you're true. Without, because it's 2 times the leading coefficient. Yeah, no constant coefficient. Okay. Yeah. Thank you. So again, we get stabilization. And the third, it's called critical damping when the determinant is 0. And the third case is where both solutions are, so where the discriminant is smaller than 0. In this case, so discriminant is beta squared minus 4mk is smaller than 0. In this case, we have two complex solutions. So lambda 1, 2 is alpha plus minus beta I beta, where alpha and beta are real. And we know that then x1, xt, so xt is then some constant times cosine of alpha. No, it's not cosine. So what are the real, let's go slower. So what are the real solutions to this differential equation? So e to lambda 1, 2 is e to alpha plus minus I beta. So what are real solutions? it's not just cosine beta t, but it's also, so this alpha t, e to alpha t is already real, so it remains. So it's e to alpha t times cosine beta t. This is the real part, and the imaginary part still e to alpha t remains times sine beta t. So these are two solutions, x1 and x2. And in this case, so x of t is then c times e to alpha t. I will factor out e to alpha t in advance, so e to alpha t, and then in the parentheses we have c times cosine beta t plus d times sine beta t. What kind of a motion is this? X of t is e to alpha t times these brackets. So what kind of motion is here inside these brackets? If we didn't have this e to alpha t, what kind of motion would this be? Periodic motion. But the amplitude of this motion is changing all the time. And what's happening with this amplitude as t goes to infinity? Yeah, we expect that it's getting smaller. So we expect, because we have damping, we expect that it's getting smaller, it goes to 0. But for this, we need that alpha is smaller than 0. Why? Why is alpha smaller than 0? Where can we see this? So still, lambda 1, lambda 2 is minus beta plus minus square root of beta squared minus 4 mk over 2a. 2m, sorry. Thank you, 2m. So why is alpha smaller than 0? Yeah, plus the real part of this beta squared minus 4mk. But so alpha is real part of lambda. Real part of lambda is minus beta over 2m plus the real part of square root of beta squared minus 4mk over 2m. So why is real part of beta squared minus 4mk smaller than beta? So what we need, so alpha is smaller than 0 if and only if the real part of square root of beta squared minus 4mk is smaller than beta. It's not that obvious to see, but there is one trick with which we can easier see this. So lambda 1 is minus beta plus square root of beta squared minus mk 4mk over 2m. And lambda 2 is minus beta minus square root of beta squared minus m 4mk over 2m. So how would we see that alpha is? So this is explicit formula for lambda 1 and lambda 2. On the other hand, we wrote lambda 1 is alpha plus I times beta. This was not a good choice because beta and beta don't have anything together. So this beta, I will write beta tilde. So here I will write lambda 1, lambda 2 is alpha plus I beta tilde because it's not the beta from the damping factor. It's not a good choice of the notation. So we have alpha plus I times beta tilde and alpha minus I times beta tilde. So how do we see that alpha is smaller than 0? What can we do with lambda 1 and lambda 2 to get alpha? Sum them, yeah. So if we sum them together, so summing, yeah, it's true. Yeah. So we get on the left hand side, we get minus 2 times beta over 2m over 2m. While on the right hand side, we get 2 alpha. And we see that from here, we see that alpha is negative. So it goes, in this case, it goes for, it really goes for negative alpha, and the motion stabilizes. So the amplitude goes to 0. Okay, so when we have damping, we expect that in the infinity, the pendulum will stop. And we have 2 more cases to finish this hour. And now I will really jump to slides and comment the situation on slides because it would require a lot of computation if we did it in detail. So the first case was free vibration without damping. The motion is periodic. The second case is free vibration with damping. So the damping force is proportional to the velocity. We have 3 cases of damping, depending on the discriminant of the characteristic polynomial. But in all 3 cases, when t goes to infinity, the displacement goes to 0. And then the third case is forced vibration without damping. So this means that we don't take into account damping, but we have a constant force acting on our body. So this is f of t. But this this force constantly acts on our body, but it doesn't need to be the same in size all the time. So its force, its size is modeled by this function f of t. In this case, the differential equation is mx double prime plus kx is equal to f of t. The solution of the homogeneous part is what we did before. So it's periodic motion. It's some linear combination of cosine and sine. And then we have a particular solution, which depends on the function f. Here we have an example where the function is of the form a times sine mu t. And here is where the resonance enters. So trying to solve this part for mu different than w, everything works fine. So what do you expect to be the particular solution? What would be the form of the particular solution if f is a times sine mu t? So we have this differential equation, second order differential equation, and the right hand side is of the form a times sine mu t. And yes, some trigonometric function. So if the right hand side is sine mu t, then it's some trigonometric function. It's a linear combination. We can try with a linear combination of sine and cosine with the same coefficient. So we can try it with this sine mu and cosine mu. And if mu is different than w, this really gives us a particular solution. And what will happen with the motion? Yeah, the motion will be periodic. So the first motion is periodic. So the homogeneous part, the solution to the homogeneous part is periodic function. The solution to the particular part, to the non-homogeneous part, is periodic motion. So we have some superposition of two periodic motions. So it will be a periodic motion with the same amplitude. So what about if this mu is exactly w? Why doesn't this work? So if mu is exactly w, why this solution a times sine mu t plus b cosine mu t won't be appropriate? Yes, so it's the solution of the homogeneous part. And as we saw today, the first hour, or even at the beginning, the end of last lecture, in this case, we have to add this t. In case where mu is exactly the same to w, we have to add this t, multiply the particular solution with t. And when we are trying to solve this, so yeah, we are trying to determine a and b, we will determine a and b. It will be possible. And what will happen with the motion as t goes to infinity? So what's happening with this particular part as t goes to infinity? Yeah, it will go to infinity as well. So this is where a resonance occurs. If the force with which we act on our body has connection with this w, which is internal to the vibration, so its w is square root of k over m. If this mu is exactly w or very near to w, then the resonance can occur. And the picture is then the picture of the motion is then something like that. So this is t, this is the displacement. And so the displacement is really periodic, but it's going to infinity. So yeah, and so on. So the amplitude is getting bigger. Of course, then what happens is that some forces become too big, and the spring would just fall apart because of that. Or if you know the situation with bridges, when the resonance occurs, when the amplitude is too big, the forces are too big, and let's see. So the period, what's the factor which determines the period? From where do we see what's the period? So this is the particular solution. This is the solution of the homogeneous part. What's the period of the homogeneous part? So yeah, when omega t is 2 pi, so this is the period. So omega 2 should be 2 pi. T is 2 pi over omega. So this is the period of the homogeneous part. And the same for the particular part. So the period is 2 pi over omega. But the amplitude is growing. Okay, and the fourth case, which are not gonna work in detail, is when we have forced vibration with damping. So we have both damping and force. So then the differential equation is that one. And it turns out that in this case, for example, if we take, again, the same function as before, a times sine mu t, then this damping factor would prevail resonance to happen. So if we are trying to solve this equation, we will see that the particular part is really of this form, because in this case, the solutions are not, so this mu is not the same to W. And in this case, then the resonance cannot occur. The particular solution to this differential equation is really, in case f is sine, is really linear combination of sine and cosine. So as t goes to infinity, the motion will stabilize. Okay, this is all regarding the course material. Are there any questions? Let's see. Let's try what would happen. So homogeneous question. If we have a dE of the form x double prime ax double prime plus bx prime plus cx is equal to, let's say, cosine of t, we guess that the particular solution is equal to a times cosine of t plus b times sine of t. So you see, if we only take, we guess this, so why not only x particular of t is a times cosine of t? So you see that if we had only this particular solution and plug it into our initial differential equation, what we would get is, here we would get something times cosine. Here, where we have first derivative of x, we would get something with sine, and here we would get something with cosine. So we wouldn't know how to cancel this sign. If we don't have this x prime yet, then cosine should work yet. So without, so in this case, yeah, in this case, b in this case, b is not 0, and xp of t will not be the solution. If b was 0, as in the first hour, then this is okay. This works. Maybe some other question. Okay, if not, then this is all for the course. I suggest that we don't make a break now and just continue for another 15 minutes to start to look at the exams and maybe to solve one of the exercises and then continue next week.